Welcome back, coders. Today we're going to be solving an easy coding challenge. Let's get started. Very well. All right, I'm going to leave this for a little bit. You can pause whenever you want to, if you want to read it. What I did was take a challenge that someone sent me to help solve, and what I changed the wording. I used a generative AI just to create a very small prompt, and after that I just tweaked it a little bit, and it changed the wording and the setting and the context, but the spirit of the challenge is still there. Moreover, I added a couple more requirements to the challenge to make it a little bit more flexible when you're evaluating someone. All right, so basically I'm going to be moving this along so that you can pause and read this also. Very well.
A few moments later.
All right, so the idea is that you have a set of elements that need to decay. Your department is understaffed, and you're basically the only person who can make these elements decay. You can only make one element decay per day, and what you do basically when an element decays is you halve it, or you take away half, or as close to half as possible. All right, and what I'm showing you now is a small run I made, and I made 5 solutions, right? And I try to put myself in the shoes of someone who's novice, someone who's in intermediate, and someone who's more advanced, so who knows more about the language. Those are the first 3 solutions you see down here. These solutions are naive solutions, so they're just taking the problem as is, trying to solve it one step at a time and without going deeper into what you can do. And then you have a couple more which are intermediate and advanced, and these go into more optimized ways of solving this problem, right? So let's start by going through the novice solution, right? So I'm just calling the novice solution here. All of this is just to show you this little graph right here. For the test input, I have a few that I've tested. For example, this one is just all of the elements weigh 50, right? And this will give you something like this. If you instead say, look, I'm gonna make them all different. These are the numbers from 1 to 99. And if you run this, let me see, IntelliJ takes like 10,000 years to do. I usually use NetBeans, but I know you guys like IntelliJ. All right, so when all of them are different, more or less, this is what you get, right? These bars are scaled to the number of elements in the set, right? So if you have more elements, you would see this move up. This one is always 100%, and these are a fraction of what the naive novice solution is. So if this takes 1 second and this takes half a second, well, this is 50%. So this is what this bar chart represents. All right, let's go to the solution. First of all, you have a set, right? You have to calculate a couple things. The first thing you need to do is say, okay, you need to give me the optimal sequence of elements that you're going to make decay, and which elements decay that day, and at the end, the sum of your inventory. And finally, the third one is, this is for the extra bit I added. You need to give me the number of days to get all the elements reduced to 1, right? And if we see, for example, I don't know if we saw the example here. Yeah, it's 27, 9, and 5 days, right? So let's try that one, which is this one and this one. And if we run it, we should be getting something similar to what the problem statement gave us. So we have this, you have your days. First day you have 20, your remainder is 10. The second day you have the 10, you keep 5. Then you have this 9 and you get a 5. You have the 7, you get a 4. You have the 5, whichever 5 you find, and you get a 3. After 5 days, the total you have is 12, right? And then you keep going until all your elements are 1. So at the end of the 12th day, you get that all your elements have decayed to their irreducible form, right? This is the naive novice. This is the naive intermediate. It's exactly the same. It just takes a little bit less. This is the naive advanced. This might be the fastest, but not the most optimal. So then you have the intermediate one, which has a little bit more elegance in the solution, but it's not the fastest. It's just more readable, more maintainable. It's better than the naive solution. And finally, we get the advanced version. And if you see here, it gives you almost exactly the same. But for instance, all of them give you 6, 7, 8, 9, 10, 11, 12. You can see all the days. This one says, okay, day 6, you do this. Day 7, you do this. We skip day 8 because 8 and 9 are the same. So at the end of day 9, you have 3 2 times. So this is just optimizing and not giving you every single day, which you could. You could say day 8 have 3, day 9 have 3, and do them both in the same step. But I chose to compress that information here, saying, look, at the end of day 9, you have 3 2 times, and then you get this result. And then we skip 3 days. So from 9, you jump to 12. Because 10, 11, and 12 are having the 2 you have 3 times. So this one is the more space efficient, and depending on your input, it might be also the fastest in most cases, not in every case. So if you have a lot of repetition in your in the weights of your elements, then this is for sure the fastest, because you get well, I showed you when I had all of them at 50. If all of them are 50, you just make all of them decay. You say, okay, 5 days, I pick 5 of those and make them decay. All right, so let's try again. And this is 27.9. Yeah, so this is it, right? So let's go through the code, and hopefully I'll try to make it easy to understand. But more or less, it's all 5 solutions are more or less the same, except the last one, the advanced one. I'm gonna probably put the chapters here so that you can jump between one and the other, so that you can compare the different parts of each solution. All right, so we got our elements. We say they give us how many days we want the forecast for. And what I'm doing here is making a defensive copy of the elements in this array, just to not modify them for the next call. If you have a single call, you don't have to do this. All right, the first thing I'm gonna do is check my input. So when you're doing a coding challenge in front of a recruiter or technical interview, you want to make sure that you check your input. You check that what kind of corner cases can you have when you get your input. This is an example of one. Maybe all your elements are already 1. So what I'm doing here is saying, okay, let me check if all of them are already 1. I'm checking if the I'm assuming that all the elements are one, and if I find that any of those is not one, then it's not in its minimum form, right? So if it's the minimum, so none of them are higher than one, then I'll just say, look, all the elements are already at their minimum, and I don't have to do anything. I cannot make them decay anymore. If that's not the case, so if we have any element that is different from one, then I'm gonna say, okay, I might not be able to make the elements decay for the number of days they give me. So if I put 5 and I only have 3 elements, 1, 1, and 2, I can only make 1 element decay. So the other 4 days, I won't get a different result. So in this case, I'm gonna calculate the days, the real days I took, and I will try to do it the number of days they tell me. But in the end, I'm gonna have the real number of days, which might or might not be equal to the number of days that I get as an input. All right, for each day, the way I solved this, I wrote a very small plan, like up here, and I said, okay, for each day, I'm gonna find the maximum, because the problem that you want to solve is how to get the minimum sum for all that set. If you want to minimize the total, you have to maximize the decay. In order to maximize the decay, you need to always pick the biggest one to halve it. All right, so each day find the maximum, halve the element, and at the end sum the result. That's the first part. Find the optimal solution, give me which elements are being halved each day, give me the total sum at the end, and the part I added after is keep going until all the elements are one. Right? So there you go. So you have 2 distinct but similar parts to the problem. In this case, we check that if they're not all one, then for each day, as I said, I'm going to find the maximum. I'm going to assume the maximum is the minimum integer, and that there is no maximum. And you're going to take this, your copy of the input, and you're going to try to see, okay, if the current maximum is less than the current item I'm checking, surely this item is bigger. So what I'm going to say is, okay, this is the new maximum, and this is the index where you can find that new maximum. You can see this is a simple for loop, doing that for each day, and I'm going through each item in the array to find the maximum. Right? So, and this is the novice solution for the naive solution. Right? So this is why we have nested for loops here. All right, I'm gonna check still. Look, if the maximum is 1, that means I cannot have each any element anymore. If the maximum in the whole set is 1, all of them are 1. Right? And I have reached the minimum I can reach at any point. Right? If I reach that minimum, there's no point in going over more days, because I got to the maximum number of iterations I can do to make the elements decay. All right? If I haven't gotten to the end, that means I can say, okay, I'm gonna halve it 1 more day. This is the number of times I have made elements decay, basically. I'm gonna take whatever it was that was there before at the index of the maximum element, and I'm gonna take that maximum and just take half. Right? I'm gonna try to get as close to half as I can, and I'm gonna subtract it from the current value. So if it's 25, I'm going to be subtracting 12, basically, and you're gonna be left with 13. 25 divided by 2 is 12. There was 25 here. The new number at that position is gonna be 13. One of the requisites in the solution was to say, okay, tell me which items you're halving each day. I'm gonna keep doing this until I either reach the desired number of days, or I get to a point where I cannot make any more elements decay. Now I have to, I finished the first part, right, of the evaluation criteria. I can give you a list of the optimal way to make items decay. Now we're going to give you the sum after this procedure. This is just for formatting, so this is the sum string to give you this nice sum here. I'm just taking for each item in the elements. If it's the first item, I'm just gonna take this empty string and add the weight of the element. And if it's not the first one, then that means there was a previous item. I'm gonna concatenate this plus sign and the current value. So that's why you get, for the first one, you get 5. For the next one, you concatenate this. And for the third one, you concatenate this. While I'm doing that, I'm building that string. I'm also adding up the weights of the elements. Finally, I say, okay, after the real number of days I had the chance of making elements decay, I add all of these numbers and get this result. All right, so that's 2 out of 3 requisites that were covered. And then this is the final part. Keep going through the list and have them until all of them are 1. This comes from what I wrote of the plan of attack for the problem. The rest of the days, I'm gonna be counting. And while we haven't reached this minimum, I'm gonna do something very similar to what I did on top. So I'm gonna go through all the elements. I'm gonna find the maximum. If the maximum is 1, I'm gonna say we already are at a place where it's a minimum, because we could have gotten to a minimum here in the first part, right? And if I wasn't checking, when you reach this part, this minimum wouldn't be updated. So I also need to be checking, maybe by chance the number of days you need to make elements decay is also the number of days where you reach this minimum. Okay, you find the maximum, going through all the elements, you check which one is the maximum, you check if you have reached this undecayable state, and if you haven't, then you say, okay, we can make the elements decay 1 more day. We do the same, we make the element decay, and this is just to display this extra info. This extra info is the one that is after the sum. They didn't tell me that I needed to give them which elements decayed each day until I reached the minimum. So I put it guarded with a boolean. This is here, and if I run it with false, basically what I'm saying is, okay, just give me the optimal decay for the first part where I give you the days, and for the rest, just give me the days when it reaches the absolute minimum, right? But for our purposes now, I think this gives you a little bit more insight about what I'm doing. So I'm gonna keep it here so that you all can see. All right, so we were here, and I'm gonna give you which item is being halved each of the subsequent days, right? there's going to be a point where I cannot make any more elements decay. And at that point, I'm going to tell you, okay, I took real days from the first part. In this case, I took 5 days. And the rest of the days are reach 12 in this case. So it's 7 more days. You can see them. 1, 2, 3, 4, 5, 6, 7 more days. And that's it for the naive novice solution. Pretty straightforward. No optimizations except maybe a boolean here and there to break loops and so on. And this is a perfectly valid solution. If someone sees this code, they're going to say, okay, it's a straightforward solution, maybe not the easiest to maintain, or maybe it is. It's very simple. The idea is that people reading it don't get confused, right? And that's why I at some points I put some comments saying, okay, this is what this part is doing. For the intermediate answer, we're going to be using, instead of trying to find the maximum all the time, doing this loop, we're going to be using a data structure that is always sorted. For this, I'm going to be using a priority queue, and I'm going to say, look, I want it in reverse order so that the biggest is at the beginning. And it goes from biggest to smallest. So I create my queue, and then I take all my elements with this array stream elements. I'm gonna filter any null elements that might be here. This comes back again at the first thing I told you. Sanitize your input, check corner cases, check things that might make your program fail, basically. What I'm saying here is I'm not accepting anything that is not a number. I stream all of this, I box them, I make them into objects because they were primitive ints. I create a list and I add all the elements into my priority queue. This orders the elements by weight, basically, and it's always ordered. If I remove the first one, the next first one is gonna still be the highest. All right, I'm gonna check if they're already all ones. I'm gonna peek at the first element. If this first element is equal to 1, that means we are at the minimum and we don't have to do anything. This is just mimicking what we did in the naive novice solution. And this is, again, we start with our loop for the number of days. We still have real number of days because we might be lower than the number of days, so we want to count them. The queue poll takes the first element and removes it from the priority queue. And I'm just gonna check, hey, is this 1? Because we're in a loop, we don't know if the first one. So we checked here at the beginning, but at any point during this loop, we can reach a point where we cannot make any more elements decay. Hey, is this max 1? That means we cannot make the elements decay anymore. So it's at a minimum. If it's not at a minimum, then we can make this element decay. So we count, we add the max minus at most half of it, and we tell you that we selected that element for halving. This is generating the final sum. If you compare this to the final sum we have here we have a loop that goes through all the elements, generates the string, adds them, and so on. For our case, using the priority queue, this is one of the advantages of using one of these collections, right? You can stream stuff, make it, in some cases, make it faster than looping. And why do I mean by faster? You can do this concurrently as you also do this. So you could build the string in one thread and add the numbers in another thread, both at the same time. And in the other case, you're doing them at the same time, but in that loop, right? You cannot separate in which thread that code runs. Okay, the first one. I'm gonna stream the elements that we have left. I'm gonna get their value as a string, and then I'm gonna join them with a plus. So that's gonna give you 3 plus 5, 3 plus 4 plus 5. This one is the naive one, and you can see that the intermediate is exactly the same as the naive. In this case, since the priority queue was sorted, you're gonna get them in a different sequence, right? You're gonna get 5, 4, 3. For the sum, we do something similar. Take this, we map them to a primitive again, and we just do sum. So these collections also have facilities for having sums or histograms or statistics. We report what the final sum is with those two values, and then we keep going. If you notice this one is exactly the same as the one on top, but instead of working on the int array, I'm just working on the collection, right? The same thing. I'm not looping to find the maximum. I'm just taking the first one. I still know the first one is the maximum. I'm gonna check if I can keep going. If I can't, I'm just gonna report that I can't keep going. I removed this because in my examples, they don't do anything. And this is something that was not in the requirements. So you might want to ask the interviewer if this is okay. They're gonna love that you ask these kinds of questions. All right, if we haven't reached a minimum, then we can have at least one element. So we're gonna say, okay, we took one more day to halve the elements. We do the same procedure as we did on top, and the same thing. We report which element we selected for halving, right? And at the end, I say, okay, I took these days from the first part, these days to reach the minimum, and the total is 12 days. All right, now we're gonna go to the advanced. This is the same, still the same premise as the first. This is still a naive solution, so just looping through days and looping through elements, not in the intermediate or advanced, but someone is looping to keep the set sorted or whatever. Exactly the same thing. We check that we can continue, that the elements are not all one. And for the optimal decay sequence, what I did here was, okay, I'm gonna create a record that has which day I'm at and what's the maximum for that day. And now I turned it all into a stream. So I tried to do from 0 to days minus 1. So that's what this is creating. This is basically the for loop, looping through the days. And I'm gonna create an object for that day. I'm gonna say, okay, on this day, this is the maximum. I'm gonna peek at that item, and I'm gonna say, okay, look, is the maximum 1? Because if the maximum is 1, that means the rest of the elements are 1. And to do that, I had to do a bit of a hack here to access the value of something outside of these operations inside a stream. You need to make the value final. So a final Boolean, you cannot change its value. But if this is a Boolean array with a single element, this can be final. And I'm using this little hacky way of keeping a Boolean. So I say that the value is going to be true if the maximum is 1. So we have reached this minimum. Okay, for this I'm going to also filter for only days where the maximum is above 1. So if the maximum is not above 1, I don't want to do anything. This is akin to my preemptive break from the loop. And if we can make the element decay, then this peak doesn't remove the element. It just checks the first element. I'm gonna remove this element, and what I'm gonna do is add the decayed element. So take the element, remove half of it, and put it back. And I'm also going to tell you which one I took. And at the end, I'm gonna say, okay, how many days, how many of these loops did I get? That's the real number of days. And this is a nice way of checking if we are at the minimum. If the number of days is less than the number of real days, we reach the end. Actually, this is wrong. Oh, but this is wrong, and we don't use this anymore. Actually, this should be like this. So luckily the number of items.
One eternity later.
What should we do here? Oh, you should just do it like this. This was wrong. So if you do it like this, it's gonna be better. Just check the first one that is left in the queue, and if it's equal to 1, you are at a minimum. Perhaps that was left over from another way of doing it I had before, and I didn't change that line. Alright, we provide the final sum exactly in the same way as the previous solution. And we keep going through the list. This is also in the same spirit as this one. We're gonna say, okay, I'm gonna iterate now, starting from the real number of days I took. And as long as we haven't gotten to a situation where we cannot make any more elements decay, and each time I'm gonna be generating one more number. So I'm gonna start on real days, and the next is real days plus 1, real days plus 2, real days plus 3, so that I don't have to count the number of days. I'm just gonna take this, and at the end I'm gonna count how many I have. I still map this to the object, but in this case I am just looking at the first item. I'm not removing it. Still doing the same thing, just checking if we have reached a point where we cannot make any more items decay. Still only wanting to make items decay that are greater than 1. And this is exactly the same as you had it on top. So this is exactly the same. Only the starting conditions are different. You still count. These are the rest of the days until you reach a minimum, and you add them again. So this just basically changed the loop for streaming. This might not. I don't like this one, and when this comes also as a surprise, because usually you start as a novice, you get to intermediate, you feel great, then you start adding crap basically to your solutions, and you look at it and it's like, this is not the best solution. You might know the language and might know how to do hacky stuff, but for maintainability and readability, and this might work great. I mean, in some cases it's even better than the advanced solution, but as you can see, it's a bit hacky. So just having to hack the streaming functions to be able to keep it this value, I don't like it that much. All right, so we're past the naive solutions, right? We have more time. We have more time in this interview that we're doing, this code challenge, and we say, okay, now that I have an understanding of what I need to do for the solution, maybe there's something more that will help me, right? Make it more readable, more maintainable, use less memory, use fewer cycles, so your big O notation. And that shouldn't be the first priority. The first priority should be readability, maintainability, and then all the rest of the optimizations. So what I did here was say, okay, sometimes you might get elements that have the same weight, right? And it's a bit suboptimal to keep them separate, because once you sort them, you're gonna have a bunch of the same numbers at the beginning and another set of the same number after those, because they're sorted. So if you have 5, 5, 5, 4, 4, 4, they're all gonna be together. And we can compress that and say, okay, I'm not gonna have the regular set. What I'm gonna have is a histogram. I'm gonna say, okay, for elements of weight 5, I have 3 elements. For elements of weight 4, I have 2 elements. And you can compress the memory that you're using. This is not exactly true, but as we go through, you're gonna see that it opens up the options you have for solving the problem. This histogram could be smaller in memory if we have more than 2 elements of the same weight and we used a 2-dimensional array, right? Because what you're doing is basically you have 2 elements, now you have them like this. If you have 3 elements, you're still gonna use 2 because it's a map of keys and values. I have weight 5, the number of items I have is 3. You're still using 2 slots in that 2-dimensional array. All right, and we do the same thing. This doesn't change. We check that we aren't at a minimum. And in this case, we go back to the simple for loop because it's more readable than the other streaming nonsense that we had in the advanced solution. And notice now that we can have better naming. In the naive advanced solution, it was just raw processing. There's almost no nice naming of variables and so on. In this case, we get, okay, once I generate my histogram, I'm gonna show you how to generate the histogram just to get it out of the way. It's not really complicated. You generate a tree map. So in a tree map, the keys are sorted and they are sorted in reverse order, just like we had in the priority queue. And then I take arrays.stream of the elements, I box them, and then I collect them, grouping by the count of times you find an element. So the function identity will give me the weight. So if I have 3 5s, I'm gonna get 5, and as a value, the number 3, because I'm counting how many times you encountered 5. I generate this map, and this is my histogram, and then I put it in this sorted map of frequencies. This will give me a map with sorted keys, descending, because it's reverse order, just like the priority queue. But it shouldn't have all the items, just the number of items, you have. So this is how you could generate the histogram. Okay, so same thing. I tried to go through the number of days they tell me to go through, but I could finish before because maybe there's no more work to do. I picked the biggest one, which is sorted, so it's the first key. I calculate what's the weight after you make the element decay. And you say, okay, for this key, compute the value as being if the value exists, so if the frequency exists, then remove it. So if it's 1, remove it. If it's not 1, then you're gonna take whatever you had there and you're gonna subtract 1. So this is basically removing one of the 5s from the map. And then you're gonna do something else. You're gonna say, okay, compute, and this is putting back the decayed element. For the weight after the decay, if it's not there, put 1. If there is a value for that, add 1 to it. So in this case, we took out a 5, we subtracted 2, we need to put back 3, right? If there's no 3 in the map, we put 1. So this is this part. If there's a value different from this, then we just add 1 more of the 3s to that one. So we keep the counts, right? We say that we have gone through another day, and we report which element was decayed. We also check if we're at the minimum, and if we have gotten to that place, we break this loop. As you can see, very simple. We have a for loop. We could make it into the stream, but this is pretty readable. I extracted this to just output the total for after n days. And this is once you start doing this, you start looking, okay, so I can optimize this out. I can take this out as a method. I can this can be static because this doesn't depend on any state of an object, right? If you don't depend on anything external and it's only internal, that's a great candidate to have a static method. Okay. And now we have the second part, which is tell me the number of days until you cannot make any more elements decay. We do the same thing, but we change the loop for a while. But the rest, it's exactly the same. We take the first key, we check if we can make this element decay. If we can make this element decay, then add 1 more day, compute the maximum for this, you remove 1 from the maximum, tell me the weight after the decay, and you put 1 more element with this new value in the map. And you could say, hey, this is great. I mean, it's readable. It looks like we're doing what's supposed to be doing. But now that we have the count of the number of elements, this opens bigger improvements, right? Yeah, and this is something that you could not have done if you had followed the naive advanced solution, because it's so hacky and complicated, and you need to follow what you're doing, that having a simpler solution gives you more chances of improving. Okay, and now we're gonna go to the advanced solution. So, and this is the advanced solution basically. And this comes back to what I told you. Hey, this is something static. This doesn't depend on anything external. Why don't I just extract it to make it more clear? So the advanced solution has readability, maintainability, and as a side effect, you can improve also the performance. What we have here is the same as we had on top, generate the histogram, exactly the same method. I'm gonna calculate the number of days that I could make elements decay, and I'm gonna make elements decay at most this number of days, and I pass it the histogram of the frequencies. And as you can see, each one of these corresponds to one of the evaluation criteria I had in my premise. And I copied them exactly 1-to-1 from the premise to this method. As you can see, I'm gonna list which elements decayed each day here. This is doing a while loop for the remaining number of days, which is hopefully the number of days that I can make items decay. Do the same thing, frequencies get first key. This is for reporting purposes, mostly just to tell you how many days I skipped, but these are the remaining days to go, right? At the beginning, if you had 5, then this would be 5. I'm gonna make element decay a maximum of this number of days. What this does is exactly the same thing you had in the other one, but instead of making it decay 1 day at a time, I can take chunks. So if I have 3 items of number 5 and I have 3 days left, I know that each day I'm gonna take 5, 5, and 5 because it's gonna be always the maximum. Instead of doing that, I can take, okay, I have 3 5s and 3 days. I'm gonna take all of these 5s, make each one of them decay each day, and I can do the forecasting of what it's gonna look like. All right, sanitizing my input again. I don't know if this frequency is a null. If it's not null, I'm gonna take the first entry for it, which is the maximum. This is the biggest item, and if we, if the key exists, so if there is a weight to this element, and there is also a value, so the value is not null, and the key is greater than 1, meaning we haven't reached a point where we cannot make any more items decay. This is also sanitizing the input and also checking that we can continue to at least make one element decay. Then you have the biggest element. Same thing, you get the weight of the element, you get how many elements you have of that weight, you get the limit that you can make items decay, and that's the minimum between the number of days they tell you that you can and the number of items that you have of that element. In this case, of the biggest element, we have this number of items. So we take the minimum between the number of items we have and the number of days we have to go, and we calculate the decay. We say, okay, when they decay, this is what's gonna be left. Same thing as before, you compute, but in this case, it is, if the frequency is exactly the day limit, we remove it. So if you have 3 items with weight 5 and 3 days to go, you remove all 3 5s and put them back after they decay. If they're not exactly the same, then what you do is you take the number of items that you have and you remove the number of days that you could make them decay. So imagine you have 3 5s, but only 2 days to go. You're not going to take the 3 5s, you're only going to take 2 of them. So you're going to take the 3 you have, the frequency, and you're going to remove the 2 days that you have to go. You will keep 1 that is not decayed. So this line removes it, and this line adds it again with the new weight after the decay. And what we're going to return here is the number of days that you told me I could make elements decay, and the days I was able to make them decay. So if you told me I had 3 and I used only 2, I'm going to return 1. There's still 1 more day that you can make this decay. And if it's not any of these, that means I didn't make any element decay. So you're still left with your days. You told me, hey, make these elements decay 5 days. I told you I can't make them decay 5 days. Why? Maybe they're at a minimum. Maybe they're all null. Maybe for some other reason that is in this filter, basically, I cannot make them decay. Maybe you didn't give me a map of frequencies, so I cannot make them decay. Here's your 5 days. Once you make them decay like that, you still have remaining days to go. So imagine we started with 5. There were 3 5s. You start with 3 days. 5 days to go. You have 3 elements with weight. Let's do 6, just not confuse them. and you have 5 days with 3 elements of weight 6. You tell me, hey, I have 5 days and this is the map. What can you do? I'll give you a 2 back. Why? Because I took the first 3 6s, biggest elements, I took them all, made them decay, and gave you 2 back. The next time I get my 2 back, I'm gonna do the same. I'm gonna say, hey, I still have days to go. Can you keep going? Maybe there's 1 3. I have 2 days to go. I'll take that 1 3, and I have 1 more day to go. And then I take 1 more item, and I'll do that until this is 0 or the number I had before is exactly the same as I have after. This is telling me, hey, I can't do anything anymore. You gave me 5 and there's something wrong. Maybe your map is wrong, maybe your the items inside the map are wrong, or maybe you just got to a minimum. Notice I didn't assume we got to a minimum in this check, but if we cannot make any progress, I'm just gonna break out of this loop because it doesn't make sense to keep going if it's always going to be the same. If everything's good and we're making progress, so what we had, the days we had before are different from the days we have remaining. I'm gonna say, okay, the real days is the number of days I took. So if I had 3 6s, I took 3 days, right? So I'm going to be adding that to the real days. And then what I'm gonna do is say, okay, at this point, I'm gonna have the chosen element, and this is how many times I made those elements decay, how many days I took to make those elements decay. And I still have the frequencies here. So that's why you see here, okay, I have 20 one time. I have 10 one time. This is how many times I took to do that. Right? And in the end, when you make these elements decay, and in this case, I'm trying to do it only once, but you return the number of days you took, right? In this case, I'm trying to make it decay at most some number of days, and I take, this is more or less the same thing, remaining and before, yeah, that's it, the times, and this is how many real days I took. For the second part, I'm gonna display the inventory. You saw this already. So this is something I took out in the previous, in the intermediate solution. And for number 3, I'm gonna, now that I have the insight of this, of make the elements decay at most this number of days, and I'm going to be displaying the number of days until total decay, when you cannot make them decay anymore. Look at this. So I'm checking if we're not at a minimum, check your input. I'm gonna count what's the rest of the days until I reach that point. Doing exactly the same as I did in the intermediate response, but I can reuse the part that I had in the previous section, and the one that was getting me the number, the number after n days. I can reuse that part also in the second part. So you see how these benefits, you have more readable code, you can reuse your code, and this is what you have seen before of this being gated with the display extra info. So, and once you get to this place, you can see, okay, this solution is exactly the same as all the rest because you're always making them decay by 1. But look at what happens when you have repeated items. So when you have repeated items, that's when the power of this small improvement really shows up. In this case, you can see, all right, you chose 120, you chose the next 20, you chose a 10, choose another 10 because when you have the two 20s, you get 10s. When you have the two 10s, you get 5s. And then the next biggest one is 9, right? And to make it decay, you need these many steps to get to the end, right? If you watch the advanced, you say, okay, I have two 20s, so make them decay by 2. And after day 2, you're gonna be left with this. You're gonna take the two 10s, and after day 4, you're gonna be left with this. Then you pick the 9. So in the naive solutions, you had 20, 20, 10, 10, 9. Now you say, hey, 20 a couple times, 10 a couple times, 9 one time. And the same happens here. Take the 7 one time, take the 5 3 times. So you jump from 6 to 9. And take the 4 one time, take the 3 3 times. You jump from 10 to 13. And then you take the 2 4 times. And that's it. You go from 13 to 17. And the solution, the results are the same. So 22 in total after n days, and you take 17 days to get to the absolute minimum. 22 for the sum, and 17 days. So this takes strides of, instead of having single loops, it takes big chunks out of your solution. And another improvement that you might not be able to see is that you're always going to be having to go to a place where all elements are 1, right? And the closer you get, the fewer distinct elements you have in your sorted map. So here we started with 3 items. We start with 20, 20, 9, and 7. 2 20s, 1 9, and 1 7. So that's 3 items. We still have 3 items, but look at what happens here. Suddenly, when you have this one, the half of 9 would be 4.5. You subtract 4. You have another 5. So this 5, the 9 we lose, but now we have one more 5. Now we have only 2 items. So the more you advance, the smaller the map, so less memory basically. And not only less memory, but sorting a smaller map is also faster, right? And we can see that this has 2 benefits. When items are repeated, and it really shines when the set of the items is huge. So I'm going to be moving away from this, and what I'm gonna do is take a random number of elements with values that go from 1 to 99, at least 15 items in the set, and I'm gonna do it for also a random number of days from 15 to 80. Okay? If you do this, you're gonna have a ton of items, and I'm gonna show you how these go. So if you see the naive solutions, these defensive copies of the array, they all stay the same size, always. You just move the number. So we have here, this is our initial conditions for the input that we have here, input stock days. So you can see input stock, this is the items that we have to, the elements that we have to decay, and we have to do it for 18 days, right? And you can see have 98, have 97, 97, 97, 96, 96, 95. When you go to the advanced, you start seeing this pattern of things going down. So this one goes down by 1, same thing, 98, 97, 97, 97, 96, 96. This is the intermediate one because it's not going in strides. then you see the map shrinks. It's shrinking, shrinking, shrinking. But you see a ton of these 15, 15, 15, 15, 15. And it's shrinking, but if you can make it, you see how big this is? If you can make it, this is 453 days, and let's wait, 453 days, yeah, have this, have that. Where is the total? Here, here's the total. There you go. This is the format, days, there you go. Day 18, you have this. Final sum after it's 3,235. And we said that we had 453 days. All right. Now you see this, you say, okay, I took the 98 one time. I took the 97 3 times. I took the 96 2 times. 95. One time, the same thing, and then it starts getting bigger as the numbers get smaller. Just the pigeonhole effect. If you pick smaller numbers, they must all land on similar numbers. As you go down, then you start seeing this go up. You see 4, 2, 3, 4, and it starts going up. 5, 4, 6, 8, 7, 10, 11, 15, 10, 11, 20, 26, 20, 31, 46, 78. So, and this is the number of items you had, 78 items. You still get the same response, but you can see how this drastically crunches your map down to the solution. And that shouldn't be the goal, but if you can get it, you know that's a good solution. In this case, this solution shines when there's a lot of items, or when the items have or when they are repeated items. But regardless of whether the initial conditions have repeated items, you know you will get to a point where you have a lot of repeated items, and that's because of that pigeonholing effect that I was telling you. So you have so many numbers between 1 and 9, right? And the smaller the numbers, then they will have to land in one of those. When you have them, they're gonna land in 1 to 5. If you have them, they're gonna land in 1 to 3, and so on. All right, and that was basically the rundown of how when I evaluate someone in an interview, I check, okay, does this solution fall into the naive novice, naive intermediate, naive advanced, or maybe, as you saw, if you go down here, in this case, the naive advanced is gonna take a lot more, but there are, this might not be right. Did I change?
12 seconds later.
This had 19 items only. So again, 73 items. Yeah, this is more or less what you expect. Like, this takes a long time, then less time, and it's diminishing returns. So there's so much that you can optimize after you choose a specific solution. Then the intermediate one, which is readable, really good, still goes day by day, like this one. It's better than this one because it still goes day by day, but it uses a more efficient data structure. And then you have this one, which, depending on how many repeats and how big your set is, it's gonna be better when you have bigger sets and more repeated numbers. All right, for 73 items, random items, you have this. So I was saying, when I evaluate a candidate, I go through, okay, is this naive novice, naive intermediate, naive advanced, maybe intermediate? It's still the naive novice solution, but with fancier data structures that give it this little edge to go from this to this, right? And then I can ask them later, okay, what would you do to improve it? And if they give me that kind of solution, very naive, novice, nothing, and they say, well, I could use a data structure that allows me to not waste time sorting or finding the maximum. For example, I could use a priority queue, I could use something else. I would say, okay, you coded the naive novice, but I see that you might be in the intermediate category. And the same thing, if they go and code the intermediate one, they're still going day by day, one by one. I can ask them, what would you do to improve it? And if they say, okay, maybe I have repeated numbers, so I can try to make this, instead of taking 1 day at a time, take n days at a time, as long as the n is smaller than the number of days I have left, I have remaining, and so on. And I can see, okay, you coded intermediate, but you gave me the solution for the advanced. So I'm gonna see you as advanced. And then I can make little tweaks to the question, because this is the requirement now, but you're gonna have requirements later that might change the code you already have running. What I do in those cases is say, okay, and in this case, the elements always decay at the same rate. You always have the element. What would happen if each element decayed at a different rate? And the solution for that, I'm gonna give it to you. You need to keep, instead of single numbers, you need to keep a record or some kind of structure that keeps the weight of the element, the rate of decay, and a forecast for that element. Like, if this element were to decay, how much would be left? And that's how you would compare the two elements, because you need to choose the element that decays faster. In this case, all of them decay at the same time. Doesn't matter which one you pick. So you pick the one that decays the most. So the biggest item decays more. When you have a variable rate of decay, it might still be true that the highest item decays more, because it's so high that it doesn't matter how small the decay rate is, it wins against all the rest. Or you might have an item that is not so big, so you don't have a lot of it in the weight, but the rate of decay is so high that you would take a big chunk out of the total that you're looking for. And all right, that's it. If you have any questions or comments, leave them below, and I'll catch you next time. Happy coding.